So today we have the Distinction Lecture Tour, Consult Distinction Lecture Tour, and also the seminar of the Institute of Computing. Our speaker will be Professor Fabrizio Granelli. The title of the presentation will be Building Real Network Digital Twins, Scenarios and Challenges. This talk is also transmitted to the INCT project on intelligent networks and IoT, INCT Econioti, and Professor Fabrizio Granelli is a full professor at the Department of Information Engineering and Computer Science of the University of Trento. He received his laureate and PhD degree from the University of Genova in Italy in 1997-2001, respectively. He was visiting professor at the Unicamp and the University of Tokyo. He was a Tripoli Consult Distinction Lecturer for the period 2012 to 2015 and 2021 to 2024. He was Consult Director for Online Content 2016 to 17, Delegate for Education at the IISI in 2015-2017, Consult Director for Education Service, Consult Director for Conference Development. Professor Granelli was General Chair or TCP Chair for several prestigious IEEE conferences such as IEEE Globecon, and FV-SDN, and CAMAD. He chaired the several symposium IEEE and Globecon. He is the founder and chair of the Aerial Communication Emerging Technology Initiative of the IEEE Communication Society and chair of the IEEE P1954 Standard Working Group. He is author and co-author of more than 300 papers, published in international journals, books, and conferences. He was Associate Editor-in-Chief of IEEE Communication Surveys and Tutorials, and Senior Editor of IEEE Transaction Green Communication Network. So, welcome, Professor Fabrizio, and thanks for the talk.
Thank you very much, Nelson, and thank all of you for coming. It's always a pleasure to come here and present my latest activities, and in this case I selected a topic that actually I started pushing from several years, and we finally start to have some interesting results. So I will speak about network digital twins. So there is a sort of unclarity in some of the journals about what is a digital twin in general, before going into network digital twin. And the thing is, a digital twin is a digital copy. When I say that it's a digital copy of something that is real. So it's a softwareized version of something that is real. I can have a digital twin of a chair, of a table, of a car, of an airplane. But the important thing, and that is one of the major features, is that it is not only a model, it is continuously fed with information from the real twin, from the physical twin. So a lot of works they simplify this aspect that instead is the most characterizing difference between a digital twin and a digital model. A digital model is something that I build imitating something in reality, and I can play with that. Of course, it has a lot of usage, but the digital twin differs in the fact that it is in real time, in principle, synchronized with the real twin. So if I have a real airplane, for example, and I build the digital twin of the airplane, the sensors that are on the airplane continuously send data to the digital version of the airplane. So they are both synchronized, and that is the real power behind the digital twin, because in this case it is not only a model or an abstraction, but it is a realistic copy of the real system. And I believe that it's important when we define digital twins to remember that, of course, there are three aspects. One is, of course, a physical entity in the real space that we start, like the airplane, for example. Then we build the digital twin in software form, so the digital version, the digital twin of the airplane. But there is a third entity that, in some cases, it is forgotten. That is actually, in my opinion, the most interesting aspect. That is, there is a data link that continuously coordinates the two. Okay. In some cases, there can be even data coming backward. So not only from the physical to the digital, but maybe even from the digital to the physical. I will maybe tell you a few words about it later. But what is important is that the digital twin, at any time, it should represent the state of the real system, okay? What is doing, what is happening in the real system. So the distinctive feature actually is this communication link. And this makes the digital twin a topic that is very interesting for me because I'm working in communications. So on one side, I'm interested in digital twins because it's an application of communication. Because of course, for example, we will discuss about 5G, 6G later on. Some people say that 5G will be an enabler to have more powerful and more distributed digital twins. Also not for networking application, but for other kind of scenarios that maybe are already successful. For example, digital twins are already being used to study predictive maintenance for cars, for airplanes, I mentioned already, and in all systems where it's important, to have real-time knowledge. It's not only planning, but it is, I have an exact copy of what is the real system at any time during its lifetime. So that will be a very important aspect, also because by itself, generating a digital twin already embeds a challenge in terms of how much bandwidth will I need to connect the physical and the digital twin, what about latency and other things. I will go a little bit more in depth, more for network digital twins because they are a more advanced, let's say, version, in my opinion, of digital twins, but they are also valid for general digital twinning. One of the reasons why the digital twin is so popular today is that it is one of the, let's say, aspects of digitalization of the real world, because today, most information is digital, because today probably all the knowledge, everything that was ever written or recorded is available in digital format. But also we are now building what some people call this metaverse or virtual reality, that is based on the idea that we can have maybe a different reality, but built with realistic devices, or maybe even digital copies of real objects that we have in reality. So in the real space we can have services, maybe infrastructure, maybe also, for example, renewable sources that we can rebuild in the digital twinning domain. And that is one of the important aspects. We need what here I mentioned as a cyber-physical interaction layer. So we need a proper way to communicate between the real space where we have the physical twins and what I call the digital twin layer, which is where we have the digital twin instances. Once everything becomes digital, so it's like the middle of the hourglass, then we can open a new world of possible applications. I will show you some of them, but in general, to be a little bit more technical, there are three big areas, in my opinion, of development of digital twins. One is you can apply the digital twin concept to study what is called what-if scenarios. Because I know now, for example, that my car is going well. What happens if, I don't know, I go faster or slower for a long amount of time, or start braking a lot? What will happen to my brakes? Will it be efficient or not? Or what happens if I crash, for example? It's something that, of course, I can do in the real world, but it's at least expensive, okay? Maybe not dangerous on the, with the proper way, but it's still costly. So I can use it for simulating somehow what might happen in the future, and also implement scenarios that maybe are very rare, okay? There are scenarios that are very expensive to simulate, and if I have a good model that is properly synchronized, this can open the floor for studying maybe which is the best action over a set of potential actions that I can take, okay? I will show you some of these examples. And one natural application is to use the digital twin of a system for generating data for artificial intelligence and machine learning training. Because, today there is a lot of enthusiasm around machine learning and artificial intelligence. Basically in all areas today we can use artificial intelligence. And the main requirement is to have a proper data set, because if I don't have a good data set, I can have wrong, let's say, outputs or strange outputs or non-reliable behavior. But sometimes it's difficult to have a data set that covers all the cases that I might think. And connecting somehow the what-if predictions with this, I can have maybe not the exact data that would happen in reality, but at least a fairly good predictive capability. And it's a software object, so I can run several digital twins in parallel, so I have not anymore the constraint of the real object, okay? Sometimes I build one object, it's very expensive, I cannot build 10 of them. Here I can multiply, of course, via software. Again, there is constraints in CPU power or memory, but still it is for sure more scalable than in reality. And one other thing that maybe today will not focus much, but because it will be a step forward, probably more for the future, will be that we can have digital twins speaking with each other. Okay, today I will focus more on the idea of focusing on a single system, building the digital twin, and let's say playing with it. But probably the more advanced idea to have multiple digital twins of different things that can interact together will make this system even more powerful. For example, I could have an interaction between the digital twin that emulates, I don't know, a base station of the mobile network with a digital twin that provides me how much energy is available to power up this digital twin with the power that is available by a windmill or a solar panel, for example. So I can mix up and add a lot of interdisciplinarity, if you want, in the mix. So it's a very, in my opinion, it's a very fascinating solution. So then coming to the point, I had a long discussion with my colleagues some years ago, before the concept of network digital twin became popular, because I read it somewhere about these digital twins, and I said, okay, I work in networks, so let's try to see if they fit. And a lot of my colleagues, finally I convinced them that they were saying, but how do you, networks are already mostly software, so how you build, a software version of a thing that is already software? If you remember what I said today, actually, there is that aspect of the connection between physical and digital twins that my colleagues did not catch at that time very well, because it's not, when I say that I want a network digital twin of an actual network, of course, I'm not saying that I want a simulator. Simulators, you are already using them, I use them for 20 years at least. But what we have here is something that also gains information about what is happening at that time in the system. So it's much more advanced in the sense that it gives me a lot of more information than a simple simulator or a simple software model. And here I just outlined a few trends that are happening already in networks, even without the digital twins, in the sense that today, because of the presence of software-defined networking, network function virtualization, the network is becoming more and more softwareized, so it's becoming a mix of different components that are all, let's say, somehow software modules. The network is also going towards automation, because we can spend some time later if you want to discuss about this, but when you introduce softwareization in the network, actually the network becomes more complex. And that is where we are today. To really gain in terms of scalability, feasibility, and cost effectiveness, you need to introduce automation. And only when it's softwareized, it can become automated, because that is the let's say the prerequisite to become automated. And automation brings a lot of benefits and reducing the costs, reducing the power maybe, and so on. So there is a trend that operators also are waiting for, to have a not fully, but at least partially automated network. And of course, AI ML for networking. I mean, several of you probably know, I discussed a little bit yesterday with Carlos, so I know some of you are working in machine learning and AI for networks. So that is a clear trend, of course, of today. But also sustainability, which is a point that I will touch in a few examples later on. Sustainability means that the network must be scalable, for example, so capable of increasing the number of users, services, traffic easily, but also to contain the consumption of resources, okay? So not only energy, but sometimes also other sources, other resources that are maybe more useful for humans than for the devices, okay? You know that today, again, we do a lot of artificial intelligence, but when you do a search, when you ask a question to one of these large language models, they say that the data center requires like 1 glass of water for cooling up. Imagine millions of requests. That is just besides the training that, you know, it's even maybe more important. So sustainability is becoming really one of the central aspects, or will be in the next years, one aspect in networking. So in this framework, the presence of the digital twin is sort of a natural, let's say, complementary technology, because it helps to somehow address all those points, because if you build a digital twin of a network, you increase the self-awareness, so you can help the network to understand what is happening inside itself, because it's like looking in a mirror, okay? The network, instead of working blindly, it can look at itself in the mirror, so it sees a copy of itself. It's like, you know, when you wake up in the morning, you don't know if you are good or not. You have to look in the mirror, okay? No one tells you. I mean, your mind cannot tell you if you are in good shape, if you forgot to raise your bird or not. So somehow there is, and in this case it's explicit, because it's a different module that you plug in the network. And then the capability of prediction is important, because there are actions that happen or situations that happen in the network at very short time scales that a human cannot even perceive. So for sure, being capable of predicting a situation, even in the short term, is very important, because we can take, for example, a mitigation action, or we can start already acting before maybe a damage is done, like a congestion comes or an attack is happening. Another thing that is important, I will come into that maybe later a little bit, is the capability of handling heterogeneity, because a clear path again in networks is that networks are becoming more and more heterogeneous, because by softwareizing we make the networks very, let's say, easy to modify. So we are going to have networks that will be maybe similar, but with different features, with different functionalities, with different hardware maybe. So there will be the need to catch up and introduce the heterogeneity as a point of advantage, not a disadvantage. And of course, again, the digital twin is not by default only one. It can be, you can have different digital twins for different islands in the network, or even different devices if you want. And of course, then again, like the capability of analyzing what-if scenarios is very important, because it can allow, for example, to train an algorithm, because you can check and have a good estimate of the outcome of an action, maybe try more in parallel and select the one that is most appropriate. So all these things, I believe, they go in the same direction, not necessarily requiring digital twins, but there are scenarios where the digital twins of the network can become handy. So I will present you a few examples. The first one is a project that I'm coordinating in the European Union on 6G. You know, in Europe we have a big investment on the road from 5G to 6G, and there are several projects in parallel that are exploring different areas. This project that I will present you briefly is targeting a few aspects. One is the digital twinning, and the other is security, basically. So the idea is to see what happens if we have digital twins in the framework of automated reaction to security threats. And so a few words about 6G. I mean, probably you know, 5G is the small triangle now there, so we assume we already have 5G fully operating, which is not the truth maybe everywhere, but at least it's, there are releases of the standard that address the three main scenarios, that is immersive communication, massive communications, and ultra reliable and very low latency. But in 6G, they want to do more, so instead of a triangle it becomes an hexagon, because we want also to address ubiquitous connectivity. That is probably where non-terrestrial networks will fit very well. AI and communication, because for sure somehow machine learning or AI will enter the picture, and also, you know, novel technology like integrated sensing and communications and so on. So in this framework, the problem is that already with 5G, especially the core of the network is fully softwareized. So, you know, there is the service-based architecture that is a fully NFV-based approach, and also a very easy to extend system, because you can add application functions or other kind of external services to extend the functionality of 5G. And this makes the so-called attack perimeter, if you want, attack surface of the system very wide. So in 5G, we inherit security threats from the traditional networks like denial of service, man in the middle, that are already tricky. But we can have unexpected attacks, because we don't know, maybe someone might find a bug in the way an interface is built. By the way, we tested, and there are some bugs in principle, in some implementation, at least the first implementations. So it's important to have a system that not only reacts to known threats, but it can react also to unknown threats. And here is where we built a very complex system, because this is our architecture. But the whole system is built on top of 5G at the moment, because of course 6G does not exist. But to simplify this overall picture, we have this. So what we propose is, this is the network digital twin. So we have a block. Well, actually we have two different digital twins. So I will come in a minute to that. Then we have a specific monitoring set of monitoring modules, because again we need this continuous connection and data coming from the physical twins. And then we also do, in parallel, we do also a real-time analysis of the context. So the part on the top is a threat detector. Okay, so in real time, besides sending data to the digital twin, we also have a real, let's say, threat detector. And then we have, of course, this is not maybe very relevant today, but we have a set of modules that cope with the heterogeneity. So these are modules that allow to put an action in on the infrastructure, but depending on the different technologies that you have in different parts of the network. And one of the most interesting part is the part on the top where there is AI that is used to filter the decisions or the detections of the threat and tries to identify the mitigation action to cancel the threat. Okay, so basically what happens is either from the real analysis or from the digital twin, you get the doubt that there might be a problem in the network, maybe an anomaly, maybe a specific attack. There is a module that where there is artificial intelligence that will check between different mitigation actions which one to select to be able to reduce the threat or delete it directly. Okay, so we try to predict even the presence of an attack so that we can cancel it even before it happens. Okay, it's growing, but maybe we can delete it in real time. Another way, if you want to look at the system, maybe it's this one. So we have the module that is handling the execution, but it follows the order of a recommender. And what the network digital twin does in this case is this one. So it can help to emulate the context because it can be used to train AI, for example, because your network changes and you can retrain if you want AI better, or something happens and you want to somehow refine your training. It can provide threat prediction, so it can early perceive the presence of anomaly and signal them to the recommender. Or also, the network digital twin, at the moment we have two different digital twins. One is called impact analysis, so it can predict what is the impact of an action. Okay, so in some cases, the digital twin triggers the recommender. In some cases, the recommender triggers the digital twin to learn what might be the outcome of an action. Okay, so that I don't need to test in the real network, but I test it on the simulator. And this, of course, makes it faster, in principle. We will see when we finish the project if we can really go that fast, but we'll go in a minute to this problem. But also more efficient, because I can test several options in parallel and at least know which are reasonable, which are not. Because in principle, the digital twin should have should be a perfect mirror of the current version and state of your network. And then, of course, we have also the real version, where the real-time threat detector is like a machine learning scheme that continuously, to process data from the flows in the network, the statistics and things like that. So, just to show you how it works, I can show you this, for example. This one is with the network digital twin. So this is to explain you how the situation works. So you start from measurements that are filtered, of course, because we need just a subset. Then there is this part called column is where there is the digital twin. It's called SAN because it's sandbox. We call it sandbox. So it's an isolated place where we can do whatever we want and it will not affect the rest of the system. So, for example, the data triggers the first digital twin that is the one responsible for threat prediction. And if the digital twin identifies the presence of I think it's this one. If this is the digital twin that looks to search for threat prediction. If it finds the potential presence of a threat, it will trigger the recommendation There are a few modules, but basically it's an AI algorithm that will generate an intent. So it will say, I would like to solve a denial of service attack to this module. And this will generate some mitigation actions that are what-if scenarios that are fed to the other digital twin that will tell which is the most successful. Okay, so this is just to explain you not all the details, but you have a loop where you predict using the digital twin. You have a loop where you analyze the potential impact of your actions. Then you decide which is the best and you implement it. Those are the modules responsible for implementation. And then the actions, of course, are selected, defined, translated, and then sent back to the infrastructure. So this is exactly the same even without digital twins. This is without digital twin. What you do is you have a real-time detector. It will detect threats, define which is the attack, but then you see here you don't have the possibility to understand which is the potential attack. So typically we use this logic when this attack happened already. So we know already which was the best solution. Otherwise, it's advisable to use the digital twin in the loop. Okay? And as you see, the presence of the digital twin is, let's say, relatively transparent, and it is interesting because it allows you to have a more refined vision of the scenario, basically, and it helps you to predict and to avoid taking wrong actions. Sometimes there are attacks that if you react, it's even worse, because maybe, I don't know, you close the firewall or you do something, for example, in a denial of service attack to the DNS, you can ask the DNS to lower the response rate, is one of the options, because this will mitigate the amount of traffic that instead will overload the DNS. So there are a few actions that maybe are not so immediate, but here we can test as many as we want, okay? And so we find the one even adapt for unknown situations. We see the traffic growing, we can try different strategies for controlling the situation. Well, here I don't go too much into details. We built this using a software that we developed, which is basically Mininet, if you know, the software for SDN plus Docker containers. So we have, our digital twin is a fully softwareized and NFV SDN enabled system in which, for example, we can deploy 5G, we can deploy all kind of open source software to generate, let's say, to mimic as much as possible what's happening in the real network. This is one slide that is the bad news. The bad news is that we are studying is that it's very difficult to maintain a synchronization, because in networks, what happens is in the physical twin, let's say that you collect an amount of time, for an amount of time you collect some traces from the network because you want to replicate them in the digital twin. So imagine this T collect is the periodic time, maybe, I don't know, every minute I capture the traffic, then I stop, I capture the traffic again, because I want to continuously feed the digital twin that is on the bottom. Just very simply, I will need some time to analyze the data, because to send all the data might be very complex. Maybe I want just to tell which are the flows and which is the throughput at that time. So I will need some time to analyze the data. I will need some time to transfer the data, because the digital twin and the physical twin will be in two different locations. They can be even in the same data center, but still there is time required. And then there is some time to, let's say, initialize the digital twin, because I will need to tell which kind of flows are present, maybe the setup of the network at that time, and so on. So when I collect the data here, I require a time that here I call the synchronization time before I can play back it in the digital twin, which means that in general, the data that I play back to the digital twin is old by this amount of time, roughly. Right, of course they can vary. But the problem is, if I also want to run prediction, maybe I even delay more, because I will add some time to run machine learning, whatever is my model. So what we are trying to do actually is we are thinking about a closed loop state synchronization that we presented actually next week. It was not me, but my PhD student that was at this conference. Our idea is to reduce the synchronization time by introducing what we call a negative delay, in the sense that if we can predict effectively what happens in the future, we can turn back the clock. So in principle, we can start working with this data and the prediction, so to start predicting right after, so that we can start the playback not from here, but later. Okay, so the effect is at the end that we reduce the playback delay, of course not be less than this, but we can reduce it in principle arbitrarily. The point is that here we must be very reliable in predicting, because if we make a wrong prediction, of course, everything breaks. So what we are studying now is a closed loop approach that is this one, like from control theory, you know, there is the PID controller. So what we are implementing now is a predictor, but also a controller that controls the difference between our prediction and the real data that is being streamed from the physical twin, so that periodically we can readapt our prediction. Okay, so we do not exactly a real-time playback, but we have a playback of the prediction that is compensated by the samples of our process, of the flows, for example, as they are coming. The impact is that quite impressive, because here we are we made 10 seconds of transmission and 10 seconds of prediction. So we are every 10 seconds we are receiving new data, and we are here you see the actual data is black, and it's here in the middle. You can see it somewhere. The red data is the simple prediction, so without compensation, and you see it goes fairly well, but sometimes prediction is not so good. And the blue data is instead the prediction corrected with the proportional, integral, and derivative compensation. Of course, in the picture is just to show you the idea. If you measure the error, it is a mean absolute error in terms of throughput estimation, and it goes from 3 points to 1.5. Okay, so this presence of the closed loop improves a lot our performance. Maybe even better, because now we're using very simple time estimator, so maybe we can do even better. But it shows you that by operating with this periodical compensation, we can maintain, you see, the reason I put this graph is to show you that the prediction is relatively stable. I mean, it does not generate weird patterns or it diverges. Typically, it remains convergent and with a very low error. So this is a path that we are following. We are going to experiment it in more diverse situations, diverse topology, because we believe that it's a way to get around the problem of the delay in the synchronization, because that is a physical problem. Okay, so the only way to go faster than light, you know, is predicting. So you have to push forward. Another scenario where it's interesting, these are for those of you that maybe were here a few years ago. I think it's partially, I presented it already, but it's important because it's a proper application of digital twins. Is, for example, the scenario of a mobile edge cloud. So when you have the capability, like 5G, should to deploy services on the edge. But focusing on energy efficiency, because, as I told you, sustainability is one of the areas that will be very important in networks. And this is the ideal scenario for digital twins, because Mac so the mobile edge cloud or mobile edge computing is a very interesting technology, and in some cases it's partially already a reality in the sense that there are some experiments that some companies did on deploying services on the edge, but by nature needs to be energy efficient because it involves the presence or the deployment of computational resources on the border of the network, which means by nature increasing complexity and increasing power consumption, because it's something that before it was not there, so for sure power increases. The point is that this should be very pervasive, because if you want to bring the services very near to the user, because you want, for example, low latency, high reliability, high throughput, and so on, you need a lot of locations, because you need to track the user, basically, and put the service in proximity. So this means several locations, so even if maybe you deploy a Mac server like a Raspberry Pi, so a small equipment, but you have to put it in a lot of locations. You need dedicated hardware because base stations are not done to host services, for example. And the other point is that they have a very extremely variable load because they follow the user. So if there is an area, for example, that in the day is very popular, but in the night no, then maybe you can turn off the devices to save power, or in the worst case, you spend money for nothing because you will not have any service running there. And the other problem is that no one knows exactly which will be the hardware, so it's difficult to have a general model that can tell you which will be the pattern of energy consumption. Maybe people will deploy very energy efficient devices, maybe not. Okay, maybe it will be one piece of PC dropped in a container, okay? And the other point is that in this case, in other cases, some people can say, oh, but we have a lot of power, who cares? Let's bring more power. Not exactly here, because on the edge, it's not easy that you have enough power. So for sure you would like to play with scarce or maybe limited power. Like I have a solar panel and I want to use it for triggering my Mac device. Okay? So in this case, as I mentioned before, there are these problems. You don't know exactly which are the hardware and software characteristics of your system. For example, you don't know which virtualization you are using, if metal, if bare metal, if you use OpenStack or Kubernetes, and all they have different energy consumption patterns, because you can have several layers, like different hypervisors and so on. The thing is, energy consumption is related only on the hardware, because at the end, everything is software, but at the end, someone has to provide the power, so it is the hardware, where you can measure the energy consumption, and the hardware in Mac should support both computation, storage, as well as communication. So, it's very interesting, because basically, this, if you think as a constraint problem, the point is that you have to find, almost in real time, the best trade-off, because you can't maximize everything. So maybe in some cases you want more computational power. Sometimes you want to use this computational power more in the communications, because you use it for switching traffic or analyzing traffic, and so on. Sometimes you want ML on the edge, so maybe you need more this, and so on. You don't know which services you are going to deploy there. So what we did is we used the same kind of idea. So this is the simple model of, this is the RAN of 5G, this is the Mac, where there is the UPF dedicated for the Mac, and this is the cloud, where there are all the other services. So very simple model. What we wanted to do is to study which are the trade-offs and whether it makes sense to have real-time information or not. So if you can optimize the system without the need to have much information, better. So what we did is we built our containers, because all these models, all these are containers in other containers, in such a way to represent, for example, the same capability of Raspberry Pi. So we took some benchmarks and we measured the capability of a container, and we constrained the container to have the same computational capability of a small device like a Raspberry Pi, just to take an example. And here we studied, here are measurements that we made. Here there is not power, but it is the relationship between the throughput that you can get against the CPU load. Because if your device has to do everything, switching, computation, storage, and whatever, then there is a trade-off. Here you can see it relatively well. Depending on, for example, in the best case, you are in the blue. Depending on how much is the CPU load, you cannot exceed a given throughput because you are bound by the capability of your CPU to handle the traffic on the bus. So this was a preliminary experiment to show that we can, even in the network, in the digital twin, let's say, of the Mac, we can have the trade-offs. So we can put constraints on the resources in order to analyze the different trade-offs. And this is an example to show you that there are some, depending on if you have two applications, the CPU usage of the first of application 2 and the throughput that is requested by application 1, there are some, depending on the amount of CPU that we give to the Mac container. So this is the power of the Mac container. And we have different feasibility regions, so you cannot exit. If you are in the worst case, you have to stay in this triangular region, because there is a region that where you cannot achieve at the same time high throughput and high computational load, because your system will break, okay, or go to too much high temperature. So we don't want that. Then we added the energy consumption, because the most interesting measurement that you cannot emulate is energy consumption. This is very difficult to emulate. So what we did is we built a real system. We used very simple smart plugs, the ones that you buy, in the supermarket, basically today. And we use different visualization technologies. Here you see bare metal, virtual machine containers. Here you have the 5G network. What we did is we used the real measurements to build the digital twins of the Mac nodes in order to optimize the system. So what we did is, here you can see some examples. We implemented different virtualization solutions, and we analyzed the energy consumption that is on the vertical, the power consumption, against data rate and CPU. Okay, you see they are different. Even looking at the naked eye, you can see that depending on the technology, they have different patterns. And then we built some algorithm to do it in real time. So here is an example where we continuously added data, and you see the model becomes better and better. So this is very wrong at the beginning, because probably there are a few outliers. But as you go on, it's more stable. And hopefully, because at the end, a real system, you cannot generate all possible situations of stress, let's say, on the real system. It's difficult to generate exactly the right amount of traffic you want and be in exactly that condition. So here we are interpolating the values that we don't have, so that we have an estimate of the points that we predict, the points that at the moment didn't yet happen. The final system looks like this, the optimization system looks like this. So we have the physical twin, we measure our indicators, which are the load for each of the Mac nodes, the throughput that is requested by the applications, and the power consumption. And then we experiment different service placement policies against a digital twin of the system, so that then we take the decision only after being filtered by the digital twin. And here are some results that we got. When there is the asterisk, means that there is a QoS violation, so the application does not work properly. Here we made the blue, it's actually blue, seems green, but it's a blue curve. The blue is the optimal allocation, so we tried all the possible combinations, and that is the best. And then there are other two curves. The orange is random, so in the orange we reallocate services randomly. So without taking care. And you see, of course, that there are some times where there is the asterisk that we fail, because of course it's random. Hopefully, that is non-trivial. Please often search against, look your results against random, because sometimes the random allocation is wonderful. So in this case, not so much, but it's still good because you see it can arrive to 80% maybe of the compliance, because the system was not under heavy load. But instead, the other approach is random allocation, but checked against the digital twin. So we didn't introduce much intelligence here. We just said, let's try 3 different random configurations and ask the digital twin which is the best. And that is the result, is the green curve. That is very near the optimal. And basically you get, instead of the optimal that of course is 100% because we build the system in order to be feasible, basically it's 99, not several nines, okay? So it's basically the same. Just by using the digital twin as let's say, a way to check before making the action, okay? So in this case, I think it shows fairly well the power of the digital twin, because in this case, it's a very complex problem, but just using random algorithms, you get basically the best possible. Let me show you a few other examples that we are working on. This is another problem that is planning the network or estimating the performance at the physical layer. What we did is we built, I hope it starts. We built a 3D reconstruction of a real part of the city. I think it should arrive, but okay, now it's coming. This is the starting, so they import the map, you see this, and then we position some base stations, and the colors represent the cover, the quality of the cover. You see the base station is here. This is a part of Trento. And you see there are the roads, the colors represent how well an area is connected or not. The reason for this is that we wanted to study, for example, what happens if you deploy drones, because the model of communication from the ground to the drone, but also from drone to drone, is not very accurate, let's say, at the moment. There are some models, but not very well tested. So we wanted to build a system that allows us to understand where there is good coverage and where we need the improvement. In this case, we can control the materials, everything, and this is actually a digital twin because the 3D data is real. They are real buildings. Okay, you can take them from OpenStreetMap. In this case, it's automated from OpenStreetMap. So what we do here is we take a part of a map that we want to study. We import it in our 3D model. Here we need GPUs for performing, because we do ray tracing. You see here there is an example. So the system performs ray tracing, which is the typical GPU, application. It was why it was born. Basically, the GPU was born, and at the end, the result is let's say an annotated map where we can estimate, for example, what happens if, I don't know, I drive a bus here, which would be the connectivity pattern. Already by itself, it's quite precise, because we use the model that is called Sionna, that was built by NVIDIA, that is very precise. But if we interpret it as a digital twin of the physical, where the physical twin is the real coverage of the network, we can make measurements. That is what we did here. We went around the city and made some measurements of signal to noise ratio. And as you see, basically there is almost a fixed difference between the simulated values and the actual measurement. So in this case, we use the concept of because this is just a feasibility study, we are going to use this idea to optimize the value, so to compensate this distance, of course only some measurement point, to achieve the digital twinning, in this case for having a very precise coverage. Okay. Also, people, I think in US, you know, there is this Coliseum testbed in Northeastern University. They are doing something similar, also with machine learning, and they can achieve 5 dB of quality, let's say, of different. And here you see we are not very far. This is without compensation 15 dB, so we can do. So in this case, the idea is to use the real measurements to compensate the simulation error, because you will use our, let's say, 3D model to interpolate basically the values that we have. Okay. One other example is this one. This is different, but just to cover also the idea of triggering, of generating data sets for machine learning. Okay. This, I don't know if you know this. This is a real data set of. I think it's going. It does not work anymore. Okay, no problem. I can use it.
Okay, thank you.
Okay, it's working? Okay. And this is a data set that was built by Stanford a few years ago. They are drones imagery. You see, there is this crossroad where people are moving, and it was an image taken from a drone. Here I show you, we are building a digital copy of the original video. This is digital. It's generated just via software. And the idea is that, you see, we have only an example with 10 people, but we can add 100, and if we have a realistic model, because I have colleagues that work in crowd modeling, you can generate an infinite set of data sets that are synthetic, but they are basically undistinguishable by the real system. This is the real image, and this is how it is augmented. And you see, you can of course then, if you don't like drones anymore, you can use it for other things, like this is can be used for behavior understanding or similar scenarios. So we are also, why this can be useful? Because in some cases you want a realistic model of the movement. This is an important aspect if you work on mobile networks and you would like to have a good model, I don't know, of the cars and the people moving around. This is a good way because you get the real traces, and basically you use the concept of digital twin, because you build a digital twin of the real scenario, but then you augment it through simulation. So it's a way to increase your data sets, because that is a big problem. To have proper data sets, you know, it's always a rare thing. So we are working on this also to generate data sets. So with this, for example, I can study how many people probably will be in the area of coverage of a drone if I want to use them for, if I want to use the drone for transmitting maybe data, or understand how likely is a person to go out of the area and things like that. We are also studying this for emergency situations. For example, if there is a small corridor and there is an emergency, how the users will queue in that system, so to know if it's suitable or not, or what to expect from emergency situations. So this is almost to complete my speech. What we are doing moving forward. One thing is now we are looking in standardization, because our main project is expected to, with the other projects in the same area, to provide hints to standardization, and we believe the network digital twin is one of the things that we would like to have in 6G. And I presented you a few applications, so how you can use digital twins for improving the training of AI ML, because you can perform data set augmentation. So not only having a digital twin, but augmenting it to, it's like a what if scenario. Okay, you have a digital twin for 10 users. What if I have 100? That is the answer. And especially for performing modeling and prediction of real system. I showed you how to model energy consumption in a Mac node or different Mac nodes, how to predict attacks, for example. Of course, they are all ongoing activities. I don't have completed these activities. In the research, in the standardization, if you are interested, there are these interesting working groups. There is ETSI-ENI, that is experiential networking intelligence, and the ETSI Zero Touch Service Management, that are the two most relevant standardization groups that can be interested in having network digital twin. In this group, we already contributed in a white paper to speak about the potential of network digital twins. Now we are studying a proof of concept to show to the people in the zero touch service management, so for using the digital twin for automation. And I have colleagues that are working with the Internet Research Task Force. There is a specific working group on digital twin of the network. They call it, strangely, in this way, digital twin network instead of network digital twin, but don't tell me why. This is the reference, and this is like a copy-paste from what they are doing now. So concluding, as you probably guessed, I think digital twinning will be an interesting technology, not right now, not just now, but also in the near future. There are a lot of other things that can be said. I mentioned the fact of linking to the idea of the metaverse that we are discussing, because it's a natural way, for example, to have a virtual reality version of what you have in reality, for example. As you saw, there are promising results. I mean, it is for sure an effective technology, but it's also a good topic for research and standardization, because, as you said, there is a lot to do. There is no, especially in the area of the network digital twin, there are very few works at the moment that are really this. I mean, if you look in the repositories, you get a lot of feedback, but most of the solutions are simulators. I mean, that are okay if you call them simulators. I don't have any problem. Of course, I use simulators for other things. Specifically in network digital twins, there is, in my opinion, a lot of space. So I encourage you to take a look, because I will share my slides, so there are a few references that you can want to check out. But if you have any question, this is my email address. So Fabrizio.Granelli@unitm.it. So I'm open now for questions, but also offline, if you like, feel free to contact me. Okay? Thank you very much.
Thank you.
So I think I'm okay. It's 5:05, so we have a little bit of time for questions.
Tem perguntas aí no chat?
Yes, please.
Hi, Fabrizio. Thank you for the presentation. I'm just curious about the part where you are collecting metrics of the real world, because the digital twin will always need feeding back from the real world. So you said that eventually you will have a collection and a retraining, I suppose, for the digital twin. But how can you ensure that part? Because I know you mentioned the delays will be an issue, a big issue for that. But also you need to include, for example, the virtualization. So you will need to assume that the real world system also has a virtualization part, or you just assume that it is always monitorable and you
Yes.
have the data.
It's a good question, yes. It's related to, I'm discussing with some colleagues that are experts in observability. Indeed, there are different ways to, and it's a good subject of research, there are different ways to synchronize the digital twin with the physical twin. What we did in the examples that was presented, the first one, the one for security, is we get basically a pickup file. So someone, I mean, who is the owner of the real network, performs TCP dump on strategic links, and then what we do is we analyze the data, we detect which are the flows, and we rebuild them on the digital twin. And we are studying how to do it well. Now we are doing it relatively well, but maybe we can do better. So one of the questions of this method is, for example, what about the privacy? Because in principle, I receive everything, okay? So that will be one point. I can maybe not use the payload, because at the moment it's not necessary for me to repeat the payload. But in some security issues, it might be good, because if someone, for example, is forging data, if I don't look at the content, it's impossible. So there will be the necessity to study. In general, yes, the digital twin expects to have a given degree of observability. Okay, let's call it like this, because one thing that also is interesting is that in principle, for example, assume that you buy a router from a company, okay, and you have your digital twin system at the device level. So each digital twin is one device. The vendor that sold me the real device could also sell me at the same time the digital twin of that device, so that I don't know how it is built, but so the communication is secured by them, so I don't look at what's happening, but I'm assured that that is a real, let's say, representation of my real system. So it's let's say, a highly reliable approximation of the real system. So somehow some digital twins might also help to maintain, for example, privacy or even patents, like in companies, because you don't need actually, what I did is very detailed. So I replicate basically the network, okay, with virtualization. So it's what I have in the testbed and what I have in my system is very similar, let's say. But my digital twin could also be a black box, because I only need to have the feedback. So in the future, maybe the owner of the vendor of an equipment will give me the digital twin and the connection, of course, so that I don't need to look what's happening, but I know that the digital twin will react correctly. And this will solve probably some of the issues of observability, because I don't need to care myself, but it's even better because if it's the vendor, it can translate the state. Okay, what I don't do here is I only use, for example, the traffic, so I don't transfer the state of the routers, because I could also have that information, how many packets are in the buffer. It's a preliminary version. If I want, I can have a full replica, but of course I need to have access to all the routers, all the systems. Here, we assume that at least we can capture the traffic. That is something that you can do on any system if you have the possibility to deploy a sensor inside. So it is a reasonable way. But of course, yes, it's an open question. Okay.
Thank you so much.
Thank you. It helped me also to describe that scenario that I think might be fascinating in the future. So maybe we have, that is why the metaverse. The idea of the metaverse is maybe you build the metaverse with digital twins of what you have in reality somehow. There are people that study these
There
things.
is another question that is hard for me to understand, like how do you scale the real needs in the world from your digital twin that is always running in a machine? So you will be limited by your resources, like the hardware resources of the thing where you are running your digital twin. So you need to scale whatever that you're trying to predict in the real world system, that maybe, for example, terabytes of information, but here you need to predict and do the escalation of something smaller, right?
Yeah, it's a good. That is another very good question. Let's say the following. It depends. Probably, especially in the network digital twin, not in the general digital twin, but maybe it's also valid in any digital twin. It depends what you use the digital twin for, because sometimes you need, maybe if I use the digital twin only for knowing the throughput that my application will get, or to predict the throughput, for example, I might maybe use a more classical simulator and just generate the input in such a way that at that time it is exactly what I believe my system is. So I get the data, and yeah, then in that case I need maybe not much data. So there will be probably, depending on the application, different trade-offs between the amount of data that you need to bring for representing the state, so for replicating and synchronizing the digital twins, and the complexity also of the digital twin itself. So there will be probably different solutions depending on what you want to achieve. Because with my, for example, my, let's say, system, since we were not sure about which kind of attacks can happen, we decided to work at packet level because most of the attacks require somehow the injection of some packets. So in principle, at least you can detect the presence of something. But again, if you are interested in maybe a larger network, this is like a private network, the one that I presented. If you are interested in a more big network, I see two possibilities. One is you build a network as a network of network digital twins. So you build small parts of your network in very high detail, and then you connect them. You can do it in principle. You generate, let's say, sockets or whatever. You can transfer data. Or the alternate version is to use different levels of abstraction. So maybe I will not care anymore about knowing that one user is generating 3 data flows, but I will have a model saying that I have from 10 to 20 users at the time and they are streaming video. I don't know if I made my point. It depends on the precision that you want. Okay, so there will be probably different solutions depending on what you want to study. For example, if I want to study the energy consumption, most likely I will need to go maybe at the device level. So maybe I will have one digital twin for the base station, one for the device that will host the UPF, the user brain function, the one that will host the Mac, because in this case I can allow the system to have different error consumption modes, let's say, or different characteristics. In my case, everything was one of the things that is important is the digital twin should be in an isolated environment. I mean, besides the connection that you want because you need to synchronize, but it should be isolated because you should be able to play with that. Okay, the idea of the sandbox there is that you have an environment of virtual machines that are detached from the rest of the network, if not only with the configuration, let's say, that they inherit. Okay. So there will be different solutions. At the moment, there is nothing written. I mean, I discussed about this in the project, for example, and we have different visions because one of the digital twins is under my responsibility, the other is under another company. And we built it in a similar way because we built like a softwareized version of the network. But for example, my colleagues that do the what-if scenario, they decided to have a loose synchronization, so just to know statistically which is the typical state of the system, or to extract it in average, and then to generate themselves the specific data. Instead, in our case, for example, we decided to replicate as much as possible the state of the system and the single packets, let's say, at packet level. So it depends on what you want to detect at the end. Probably one model can fit different scenarios, but it depends then on the complexity. These systems are, in my opinion, are easily scalable because they are all virtual machines or containers. So if you have, if you imagine that you will host these systems in a data center, probably I don't think you have problems of scaling up and down. But of course, if I do it in my laptop, I mean, I can show you, we can replicate the 5G network in the laptop with this system. But of course, if I add more than 10 users, probably it could break. I imagine. I never tried. It seems to work. Okay. Yes?
Thank you for the presentation. I just have a question about the standardization process in 5G or 6G. You mentioned that you will provide, or the group working on digital twin in Europe maybe will give some suggestions for the 3GPP or something like that. Could you mention some of the insights that you have already from the project and for example, the requirements that the digital twin needs in the network architecture or something?
Yes.
Like
So it works like this. There is all the projects in 6G, they are in a specific track of European funding. So there is a coordination among the projects, not in the sense that you change depending on what the others do, but we have periodical meetings on some aspects, like there was a set of meetings on 6G architecture, set of meetings on for example, the requirements, set of meetings on the scenarios, and so on. So what they do is there is a chair that is collecting feedback from all the groups. So they don't take decisions, but they put, you know, in parallel what the different projects believe about, or what they are doing about these things. Then what happens is there are meetings that are organized between these working groups and the working groups of 3GPP through a big project. There is a huge project that is called XAX, that is the called flagship, 6G flagship project. So this project collects everything, and then they go to 3GPP to present what they believe is common, let's say, consensus. And for example, or you can go directly. For example, I am member of the two working groups of ETSI, because it's if you are a member of ETSI, our consortium is member, so you can go in any working group and contribute. In the in the experiential networking intelligence, we proposed to include the digital twin in some levels as a feature of some levels of autonomicity of the network. So probably it will be edited in the standard as one scenario where to deploy autonomous behavior at different levels, because we don't define the network digital twin, but we find the network digital twin as a way to decide the actions, for example, to compare actions. Okay. And another thing is, for example, I mentioned in the zero-touch service management group, with some partners in the project, we will go and present a demo. So you can propose to do a demo for the working group, where you show the feasibility of, for example, how the digital twin can be integrated in 6G. So you do these steps. Then, of course, there are the 3GPP groups that will harmonize and decide finally. But that is a push towards solutions that we test in the projects.
We need to close the session. So thank you very much for this enlightening conference about digital twin. Thank you.
Thank you very much.
Obrigado a todos por